वेलकम टू वीलर्न में आपका स्वागत है। सब्जेक्ट ऑपरेशनल रिसर्च सेशन नंबर 9। टॉपिक टू बी कवर्ड इन दिस सेशन: नॉन लीनियर प्रोग्रामिंग, इंट्रोडक्शन, सॉल्यूशन ऑफ नॉन लीनियर प्रोग्रामिंग प्रॉब्लम, कॉन्वेक्स एंड कॉनकेव फंक्शंस, कोहन-टकर conditions for constraint optimization, quadratic programming and separable programming. Introduction: a linear programming problem is characterized by the presence of linear constraint and linear objective functions in decision variable. जैसा मैंने आपको पहले भी बताया था कि लीनियर प्रोग्रामिंग जो है किस तरह का होता है कि इसके लिए लीनियर कंस्ट्रेंट होना आवश्यक होती है और लीनियर ऑब्जेक्टिव फंक्शंस जो हैं डिसीजन वेरिएबल्स के टर्म्स में होने चाहिए। There are problems at real life situation where neither the objective function nor the constraint are linear functions in decision variables. For example, suppose 40 cubic meters of a granular product are to be transported across a river by ferry. Any amount of the product can be transported in one trip, and regardless of how much is transported at one time, the cost is rupees 10 per trip. The cost per square meter for the sides, bottoms and end of a container are as follows: ends rupees 20 per square meter, bottom rupees 10 per square meter, sides rupees 10 per square meters. Like this one, this is the configurations of the container, and then this problem can be formulated as a non-linear programming problems. Minimize functions of x1, x2, x3 equal to 400 upon x1, x2, x3 plus 40 x2, x3 plus 10 x1, x2 plus 20 x1, x3 subject to g x1, x2, x3 equal to 40 upon x1, x2, x3 less than equal to 30. The constraint is x1 greater than equal to 0, x2 greater than equal to 0 and x3 is also greater than equal to 0. Both the objective functions and constants stated in the example are non-linear function of the decision variables. x1, x2, x3, the solution of problems is x1 2.3 meters, x2 1 meters and x3 0.6 meters. The values of the constraint and the minimum value of the objective functions are g 2.31 0.6 which equal to 29 and g 2.31 0.6 equal to 364.6. Example: both the objective functions and the constraint stated in the examples are non-linear function of the decision variables x1, x2, x3. The solution of the problems is x1 equal to 2.3 meters, x2 equal to 1 meter and x3 equal to 0.6 meter. The values of the constraint and the minimum value of the objective functions are g 2.31 13.6 equal to 29, g 2.31 0.6 equal to 364.6. Now, solution of a non-linear programming problems. The methods of solving a linear programming problem is based on the property that the optimal solution is located at one or more extreme points of the solution space. T1 edge property enables us to limit our search to corner points of the feasible regions and thus to obtain the optimal solution in a finite number of iterations. In nonlinear programming problems, the optimal solution can be located at any point along the boundaries of the feasible region, or it can even be located within the feasible region. Due to non-linearity of the objective function and the constraint, it can be difficult in certain cases to distinguish between the local and global solution. And this is next example. Consider the following non-linear programming problem given by maximize functions of x1, x2 equal to 32x1 plus 8x2 plus x1, x2 minus 1 by 2 x1 square minus x2 square, where x1 less than equal to 80, x2 less than equal to 60, then 5x1 plus 6x2 less than equal to 600, x1 plus 2x2 less than equal to 160, and so x1 greater than equal to 0 x2 greater than equal to 0. And this is the boundary of the situation. The constraints in these problems are all linear and hence the feasible region is convex. As the objective function is non-linear, the solution is not necessarily found at an extreme point. The optimum solution is located at the point Q, where the highest profit point touches the boundaries line of the feasible region. The optimum solution is x1 equal to 72, x2 equal to 40 and f equal to 1312. A functions x1, x2, x3 and so on xn equal to function of x bar is said to be convex over a convex set S if and only if for any 2 points x and y in S. Functions of lambda x bar plus 1 minus lambda y less than equal to lambda functions x bar plus 1 minus lambda functions of y 0 less than lambda less than 1. Like this one. And our concave function. Our functions x1, x2, x3 and so on xn equal to functions of x is a concave functions over a convex set S if and only if for any 2 points x and y in S. Functions lambda x bar plus 1 minus lambda y greater than equal to lambda functions x bar plus 1 minus y 1 minus lambda functions of y 0 less than equal to lambda less than equal to 1. And now convex and concave function. Characterizations of convex and concave functions by partial derivatives. A functions f x1, x2, x3 and so on xn is a convex if and only if the matrix of second partial derivatives h x bar equal to delta 2f upon delta xi into delta xj is positive semi-defined. Likewise functions of x1, x2, x3, x4 and so on xn is concave if and only if h x bar is negative semi-definite. Example, functions of x1, x2 equal to 2x1 cube minus 6x2 square, delta f upon delta x1 equal to plus 6x1 square and delta f upon delta x2 equal to minus 12x2. So delta 2f upon delta x1 square equal to 12x1 and delta 2f upon delta x1 delta x2 equal to 0, delta 2f upon delta x square 1 equal to minus 12. Hence hx equal to 12x1 0 0 minus 12. If x1 less than equal to 0, then 12x1 less than equal to 0. Determinants of hx equal to 144, x1 greater than equal to 0. Hence hx1 is negative semi-defined for x1 less than equal to 0. Thus functions of x1, x2 is concave for x1 less than equal to 0. And now Pointtracker conditions for constraint optimization. The optimum solutions of a general nonlinear programming problems can be identified by using a set of conditions developed by Cohen and Tucker. The optimum solution of general nonlinear programming problems can be identified by using a set of conditions developed by Cohen and Tucker. These conditions are as follows. Let us define m plus n general functions of n variables x1, x2, x3, x4 and so on xn as f and g1, g2, g3, g4, gm. The general nonlinear programming is maximize functions of x1, x2, x3 and xn subject to g x1, x2, x3, x4, xn less than equal to b, where I equal to 1, 2, 3, 4, 5 and m. The set of constraints also include the non-negativity constraints, a set of necessary but not sufficient conditions for x equal to x1, x2, x3 and xn to optimal for the general nonlinear programming are as follows. Lambda g x equal to 0, I equal to 1, 2, 3, 4, 5 and so on m. So delta f upon delta xj equal to minus lambda, delta g1 upon delta xj equal to minus lambda m, and delta gm upon delta xj equal to 0, and j equal to 1, 2, 3, 4, 5 and so on, and gx less than equal to 0, I equal to 1, 2, 3, 4, 5 and m, and lambda greater than equal to 0, I equal to 1, 2, 3, 4, 5 up to m. The quantities lambda I are usually known as Lagrange multipliers. If the original problems consist of m constants and n variables, Kohn-Tucker condition would lead to m plus n variables and 3m plus n constants. Example, maximize functions of x equal to x2 subject to g1 x1 x2 equal to x1 square plus x2 square minus 4 less than equal to 0, g2 x1 x2 equal to minus x1 square plus x2 equal to less than equal to 0, and g3 x1 x2 equal to minus x1 less than equal to 0, and g4 x1 x2 equal to minus x2 less than equal to 0. The Kohn-Tucker conditions are given by x1 square plus x2 square minus 4 less than equal to 0, where minus x1 less than equal to 0, minus x1 square plus x2 less than equal to 0, minus x2 less than equal to 0, 2x1 lambda 1 minus 2x1 lambda 2 minus lambda 3 equal to 0, 2x2 lambda 1 plus lambda 2 minus lambda 4 equal to 1. So, taking common the equation lambda 1, then we have x1 square plus x2 square minus 4 equal to 0, then taking lambda 2 as a common, then minus x1 square plus x2 equal to 0. So, lambda 3xi equal to 0, lambda 4x2 equal to 0, lambda 1 greater than equal to 0, lambda 2 greater than equal to 0, lambda 3 is also greater than equal to 0, and lambda 4 is also greater than equal to 0. So, the optimum solution can be obtained by inspections as x1 equal to 1.24962, x2 equal to 1.56155, lambda 1 equal to lambda 2 equal to 0.24254, lambda 3 equal to lambda 4 equal to 0. This solution satisfies the Kohn-Tucker condition, but the solution x1 equal to 0, x2 equal to 0, lambda 1 equal to 0, lambda 2 equal to 1, lambda 3 equal to lambda 4 equal to 0, which is not optimum, also satisfy the Kohn-Tucker conditions. Now, quadratic programming. The general quadratic programming problems is given by maximize functions of f equal to summation of j equal to 1n pj xj plus summation of j equal to 1n summation of k equal to 1n djk xj xk, subject to summation of I j equal to 1n a ij xj minus bi less than equal to 0, where I equal to 1, 2, 3, 4, 5 up to m, and minus xj less than equal to 0, where j equal to 1, 2, 3, 4, 5 up to n. The quantities summation of ij equal to 1n, then summation of k equal to 1n, djk xj xk is commonly referred to as a quadratic form. If this quadratic form is negative, semi-definite and symmetric, then it is a concave functions of the decision variables. Since the constants are linear, the feasible region is convex. Thus, Kohn-Tucker conditions in this case are both necessary and sufficient. In order to derive these conditions, we use multipliers lambda I equal to 1, 2, 3, 4 up to m corresponding to the constants. So, summation of j equal to 1 and aij xj minus bi less than equal to 0 and mu j equal to 1, 2, 3, 4, 5 up to n corresponding to the non-negativity constant. Therefore, df upon dxj equal to pj plus 2 summation of k equal to 1 n djk xk, where j equal to 1, 2, 3, 4 up to n. Therefore, the dy by dxj summation of j equal to 1 n aij xj minus bi equal to aij, where I equal to 1, 2, 3 up to m and j equal to 1, 2, 3 up to n. So, si equal to bi minus summation of j equal to 1 n aij xj, where I equal to 1, 2, 3, 4 up to m. Hence, Kohn-Tucker conditions are given by pj plus 2 summation of k equal to 1 n djk xk minus summation of I equal to 1 m lambda I aij plus mu j, which is equal to 0, j equal to 1, 2, 3, 4, 5 up to n. that is minus 2 summation of k equal to 1 m djk xk plus summation of I equal to 1 m lambda I aij minus mu j equal to pj. So j equal to 1, 2, 3, 4, 5 up to n. Therefore, Si lambda I equal to 0, xj mu j equal to 0. So Si lambda I mu I j xj greater than equal to 0, where I equal to 1, 2, 3 up to m and j equal to 1, 2, 3, 4 up to n. If the conditions xi lambda equal to 0 and xj lambda j equal to 0 are ignored, a feasible solutions of the problem can be found by linear programming methods. If we ensure that the pairs lambda I sj and lambda mu j xj are not basic variables simultaneously, then the conditions si lambda equal to 0 and xj equal to 0 will be automatically satisfied. Thus, if we use simplex procedure with a restricted entry rule, any feasible solutions of the set of equations 1 and 2 will be optimum solutions of the quadratic programming problems due to sufficiency of cone-Tucker conditions. Then separable programming. Separable programming is an approximate methods of solving certain non-linear programming problems. As separable functions is one which can be expressed as the sum of subfunctions where each subfunctions is a functions of one variables only. Like this one. Example, functions of x1, x2, x3 equal to 4x1 square plus 7 x2 minus 3 ka square plus 11 e to the power x3 equal to functions of x1 plus functions of x2 plus functions of x3, where f1 x1 equal to 4x1 square, f2 x2 equal to 7 x2 minus 3 ka whole square, f3 x3 equal to 11 e to the power x3. The separable programming method is applicable if the objective functions and the various constraints are separable. The general form of separable programming problems is given by maximize f0, x1, x2, x3 and so on xn, subject to function of x1, x2, x3 and xn less than equal to bi, where I equal to 1, 2, 3, 4 m, xj greater than equal to 0, where j equal to 1, 2, 3, 4 up to n. If the objective functions and constraint are separable, then we can write f0 x1 x2 up to xn equal to summation of j equal to 1 n f0 j xj fi x1 x2 x3 up to xn equal to summation of j equal to 1 n fij xj, where I equal to 1, 2, 3, 4, 5 up to m. Thus, the problems under considerations can be expressed as maximize j equal to 1 n f0 j xj subject to summation of j equal to 1 n fij xj less than equal to b, where I equal to 1, 2, 3, 4 up to m, xj greater than equal to 0. And now do it yourself. Question number 1, define separable programming, and question number 2, define quadratic programming. And that's it from session number 8. Thank you.